Okay, lads, just going to look at 2015 question 6. Okay, it's and really I'm just going to look at one part in particular, and it's talking about derive the relationship between the period of a satellite t, the radius of its orbit, and the mass of the Earth, or the mass of the planet which the satellite is orbiting. Okay, so with any of these guys, I think it's always important either you learn them off by heart or we try and work at a bit of understanding. Now we need to really understand where we're heading with this equation, what we're looking to have at the very end. So we're looking to have t squared is equal to 4 pi squared r cubed over g m. That's what we're looking to finish this whole equation with. Now, these are always very useful, okay? So that's what we're going to keep in mind. That's where we're going to finish, and this is what we're starting with. We're trying to find out what the relationship is between t, r, and m. Okay, so first thing is we need to figure out about the t. Period of a satellite in orbit is 2 pi r, which is the circumference, over the velocity of the satellite, okay, v. Then we also know that centripetal force of a particle moving in a circle, the end of a circle, if it moves around, is given as mass times acceleration. Any force given as mass times acceleration, so F is equal to m mass times velocity squared over r, the radius. Okay, now when we talk about planets, say we've got planet 1 and planet 2, there's a force of attraction between them that pulls them together, okay, and that's called gravitational force, F, and I'm going to give that subscript G, and just go back here and give centripetal force subscript C. Fg is equal to gravitational constant times the mass of the first planet times the mass of the second planet, all over the distance between the two planets squared. So you should remember that the force of attraction between two bodies is proportional to the mass of each individual body and inversely proportional to the square distance between them. So if you think of a thing moving around a circle, so we look at our first particle here, we got a particle at the end of a circle. As that moves around, we got centripetal force pulling it in. Now, if we were to think of a planet orbiting another one, so say the Earth orbiting the Sun, or even just a satellite orbiting Earth, it's the same idea. There's gravitational force pulling this into the center, continuing it moving in a circular path, which is the exact same definition as centripetal force. Okay, so what we can do with that then is we can equate F gravitational equals to F even centripetal. Okay, so the first step in doing that is we can look at these little formulas here. Now we need to say a couple of little bits and pieces. When we talk about a satellite in orbit, we usually use capital R. Okay, and then I'm going to call the mass of the satellite mass 1. So just so they're equal. And I'm also going to say the distance between the two bodies is capital R. Okay, because that's the radius of the satellite's orbit around Earth. So now I can say Fg is equal to Fc. So G m1 m2 all over the radius of the orbit to be squared is equal to mass 1 times the velocity of the particle, which is the satellite in this case, over the radius. So there's a couple of things that are going to begin to cancel for us here. We've got a common m1 on both sides, so I can divide both sides by m1, and that will cancel with that, and that will cancel with that. Then I'm going to multiply both sides by r, and this r over here will cancel against this one here, and this one will cancel against one of these r's to make that a singular r on the bottom. Rewrite that line. What we have then is G m2, which is the mass of the Earth, over the radius of the satellite's orbit, is equal to the velocity of the satellite squared, just the velocity of the satellite squared actually, sorry, we stop there. Now, this isn't the relationship they asked us for. They actually asked us for the relationship of T, R, and M. What we have currently is a relationship between velocity, R, and M. So we're going to have to try and target this V and change it for a T. Of course, we have a formula we quoted at the very start. T squared is equal to 2 pi R over V. So just manipulate that first formula. T is equal to 2 pi R over V. So therefore, V is equal to 2 pi R over T. So every place we have a V here, we're going to put in, sorry you couldn't see that. So I just manipulated T is equal to 2 pi R over V, the first equation we started with, and we changed that into V is equal to 2 pi R over T. Just multiply across by V and divide across by T. So I'm going to put that in over here for this. And actually before I even do that, I'm going to square root both sides. Okay, so I'm going to find the square root of V squared to get that to a singular V, and then square root of that. So square root G m2, which is the mass of the Earth, over the radius of the satellite's orbit, is equal to V, which is 2 pi r over t. We want a relationship between t, r and m, and this is the form we're looking to finish with. So we can see that I need to do a little bit of work on this to manipulate this equation. So I'm going to multiply both sides by t, and that will cancel that t against that, and then I'm going to divide across by gm over r. So that will give us t is equal to 2 pi r all over root gm2 over the radius of the planet. Now, I'm going to go back here and change that to capital R because that's just the same radius that we've always been dealing with, the radius of the satellite's orbit. Okay, so we know that if we divide anything by a fraction, it's the same as multiplying by the fraction inverted. So t is actually equal to 2 pi r times r over gm2. And then what we do then, just to clean that up a little bit, is we square left and right. Okay, and we should get an answer for that. So if we square left and right, I'm running out of a bit of paper here. So we square t squared, we square everything on the right, then we end up with t squared is equal to 2 squared, which is 4, pi squared, which is 2 pi squared. So we square that, will be r squared. Square to square root will cancel, and we end up with t squared is equal to 4 pi squared times r cubed over gm.